All right, good morning. So this is our last week. Next Monday, there's not going to be any classes, okay? So we're going to finish everything this week. So this is our last 3 hours, basically, okay? All right, so today we're going to continue sensitivity analysis. Essentially, we're going to sort of wrap up the this last topic of this course. So far, we have looked at changes in the right-hand side vector B, which affects the right-hand side of the tableau, which might affect primal feasibility. Then we looked at changes in the cost coefficient C, which affects row zero coefficients, depending on whether you have a basic variable or non-basic variable whose cost coefficient is changing. Either the entire row zero changes or only the coefficient of the non-basic variable changes in row zero. So that might affect dual feasibility. Then we looked at changes in the matrix A. And we separate into 2 cases. If the change happens in the column of a non-basic variable, then that means that only the entries underneath that basic variable, that non-basic variable, sorry, will be affected. And then we said that if the change occurs in the column of a basic variable, then that's a sort of complicated issue. So as a result, we usually solve the problem from scratch because when the matrix B changes, the entire tableau changes. So that might affect primal and dual feasibility at the same time. So we may lose both primal and dual feasibility. And remember, the other issue was that the new basis matrix may not be invertible. So as a result, there might not be a corresponding basic solution. So today we're going to continue our discussion. And in particular, we're going to look at the following. So adding a new variable to an LP problem. So essentially, let's assume that we have our original primal dual pair of problems. And without loss of generality, let's assume that the primal problem is given in less than or equal to constraints with non-negative variables. And the corresponding dual problem, as we now know, is given by a minimization problem with greater than or equal to constraints and non-negative variables, okay? So this is something we have seen before. So this is the usual primal dual pair of problems. So what I'm going to do is the following. So in the primal problem, I'm going to introduce a new variable. So let me try to give some motivation about that. So, suppose that this problem corresponds to a production planning problem. So we're trying to maximize our profit. So think of B as our resources. So X is the production amounts, basically, okay, the vector of production amounts. So we have currently n products, let's say. X1 denotes the number of units of product 1, X2 denotes the number of units of product 2, and so on and so forth. So we want to maximize our profits subject to resource constraints and non-negativity constraints. Okay, so you can think of the primal problem in this way, basically. And then suppose that you're interested in the following problem. Well, I'm going to start producing a new product, for instance. Okay, so right now I'm producing n different products. So now I'm going to start producing n plus first product. Okay, so think of this as for example, if you're an automobile company or manufacturing facility, then you have n different models, and you want to introduce a new model, okay? And as a result, of course, your LP problem will change, right? So because now you have n plus 1 products. So let's think about how the problem will change. I'm going to call it P prime, okay? So the change in the primal problem will be given by the following. So I have my original variables, okay, the original objective function, plus I'm going to have the profit of the new product, which I'm going to denote by Cm plus 1. And I'm going to multiply it by Xm plus 1, which denotes the number of units of the new product that I'm going to produce. Okay? So now I have a total of n plus 1 variables. Okay, so these are the original n variables plus the n plus first variable. And then similarly, so that product will use some resources. Okay? So I'm going to add a new column to my A matrix. And I still have same resources. And then all of my variables, original variables plus the new one, should be non-negative. Okay? So essentially, if I have an LP problem, and if I want to introduce a new variable to my problem, this is exactly what I need. I need a new cost coefficient. And I need a new column. So Am plus 1 is a column vector, basically, which represents the entries underneath Xm plus 1 in my original coefficient matrix. Okay? And my original variables, which is a vector, plus a new variable, which is just a scalar variable, just a real variable, a single variable, have to be non-negative. Okay? So now what I'm going to do is the following. What is the corresponding effect on the dual problem? Well, let's think about it. So first of all, note that number of constraints will not change, basically, right? So as a result, the number of dual variables will still be the same. So I'm going to still use W for my dual variables. So what does the objective function look like? So it's going to be the same as the previous one, basically, right? So I will still have minimized WB. Now, what about the constraints? Now, one thing you should pay attention to is the following. Remember, for each column in the primal problem, there's going to be a corresponding constraint in the dual problem, right? So in other words, for each variable in the primal problem, there's a corresponding constraint in the dual problem. So if I'm adding a new variable to my primal problem, what's the corresponding effect on the dual problem? So I will add one more constraint to my dual problem, basically, right? So let's try to figure out what that constraint looks like. So first of all, I'm going to have the original constraints, because the original part does not change. So I'm going to have WA greater than or equal to C, for starters. Then what does a new constraint look like? Exactly. So I'm going to have a new constraint corresponding to this column, basically, right? This new column that I'm just going to add. So as a result, I will have W times AM plus 1 should be greater than or equal to CM plus 1. So this was a constraint which did not appear in the original problem, but it is now a part of the new dual problem. And once again, W should be non-negative, okay? So as a result, the effect of adding a new variable to the primal problem is equivalent to adding a new constraint to the dual problem, basically, okay? So by adding a new constraint to the dual problem, I'm actually making the feasible region either the same or smaller, basically, right, for the dual problem. So I'm adding one more restriction, which means that the feasible region of the new dual problem cannot be larger, right? It can either stay the same or it can be smaller, okay? Any questions so far? So essentially, think of xm plus 1 as my new product, okay? So these are the resources per unit that will be used by the new product. I still have the same resources. Then the effect of this new variable, adding a new variable to my primal problem, corresponds to adding a new constraint to the dual problem, basically, okay? Any questions so far? All right, so just like we did in sensitivity analysis, what I'm going to be interested in is the following. So now for the original problem, suppose that I have an optimal production schedule, okay? So I'm, let's say, producing 10 units of the first product, 15 units of second product, and so on and so forth. And now I'm introducing a new product, which I'm going to call M plus 1, okay? That's going to be my new product. And I'm going to be interested in the following question. So if I add this new product to my sort of production, basically, okay, then will my optimal solution for the original problem still remain the same for the new problem, okay? So in other words, if I look at the new problem with the M plus first product, basically, is it still optimal to have the same production without actually producing any M plus 1? Does that make sense? Okay? So let me repeat my question again. So essentially, suppose that I have the optimal production schedule for this problem. And obviously, the optimal production schedule does not produce any xm plus 1 because there's no xm plus 1 here, right? So when I introduce a new product, which I'm going to call or represent by xm plus 1, I'm going to be interested in the following question. So does my previous production schedule still remain optimal? Okay? Or should I actually sort of come up with a new production plan right now? Okay? Well, okay, so the question is, how are we going to determine that? Well, so first of all, let's make some observations, okay? So let X star and W star denote optimal solutions for the primal and dual problems, respectively. Okay? So essentially, I'm going to assume that X star is an optimal solution for this problem, and W star is an optimal solution for the dual problem. Keep in mind that X star is a column vector. W star is a row vector, basically, right? Okay? All right, so now my first question is the following. How can I find a feasible solution for the new problem using the optimal solution of the previous problem? Yes?
I think if Cm plus 1 is negative, then the solution before is now infeasible for the new model.
So if Cm plus 1 is negative, okay?
The optimal, the solution before
okay.
we have is now infeasible for the new model.
Okay, so why is it infeasible?
Because, yes.
So first of all, you should be careful because, remember the objective function has nothing to do with feasibility, right? So the objective function does not affect feasibility, okay? So feasibility actually depends on the constraints, okay? So my question basically is the following. So if I have an optimal solution for the original problem, an optimal production schedule for the original problem, can I find a feasible solution for the new problem? That's my question, okay? Using the optimal solution of the previous problem. Now, here's one way to think about this. So in my optimal production plan for the original problem, I'm producing, let's say, 10 units of product 1, 20 units of product 2, and so on and so forth, right? Okay? One thing you should be careful about is that, there are exactly n products here, okay? Whereas right here, we have n plus 1 products, okay? So what I'm interested in is the following. So can I find a feasible production plan for the new problem using the production plan of the original problem? So in LP terms, if I have a feasible solution for the original primal problem, can I turn it into a feasible solution for the new primal problem? So this is not a very hard question, actually. Okay? So how many variables do I have in this problem? So I have n here, plus 1 here, right? So a total of n plus 1 variables. How about this problem? I have only n variables, right? Okay. So here I need values of n plus 1 variables, whereas here I'm only using n variables, basically, right? So that's the difference between these two problems. So what I'm interested in is the following. So now I want to find values for x and xn plus 1 so that everything here will be satisfied. Okay? So my question is, can I do that using the solution of the original problem? Well, so once again, so let's think about it together. So now in my original optimal solution, okay, so think of this again as a production planning problem. So I have a vector, right, that corresponds to the number of units of each product that I'm going to produce. So x1 is the number of units of the first product, x2 is the number of the units of second product, so on and so forth. So subject to these resources and non-negativity constraints, I have my best production plan, basically, right? Okay, but using only n products. Okay. So now I have the n plus first product. Okay. And if I simply define xn plus 1 to be equal to 0, okay, and if I use the same values from the previous problem, I claim that that's going to be a feasible solution for the new problem. Let me repeat that again. So what I'm going to do is the following. I'll take the optimal solution from this problem, okay, and the optimal solution by definition, of course, is feasible for this problem, okay. So which implies that ax star is actually less than or equal to b and x star is non-negative, okay. Then what I'm going to do is I'm going to set my x equals x star in this problem, and I'm going to set my xn plus 1 equal to 0, okay. And I claim that that will be a feasible solution for this problem, okay. Well, this is pretty easy to see because essentially what I'm going to do is I'll just copy the same production schedule and I'm going to set xn plus 1 equals 0. What does that mean? So that means that I'm going to pretend that xn plus 1 does not exist in some sense. Okay? Well, if I do that, then this problem is just reduced to this problem, basically, right? Is that clear? Okay? So then this implies that the solution, I'm going to call it x bar, and the first n components will be the same as x star, and the last component is equal to 0. So now this is an n plus 1 dimensional vector, okay? So then x bar is a feasible solution for the new problem. So before I move on, I just want to make sure that this is clear. So any questions about this? So essentially what I'm doing is the following. Using an optimal solution of the original problem, I'm actually constructing a feasible solution for the new problem. Okay? I'm not saying that that's necessarily optimal for this problem, but I'm just saying that that's a feasible solution for this problem. Okay? And intuitively this makes sense. Essentially, I'm introducing a new product, but I'm not producing anything yet. Okay, so that means that I'm just sort of sticking to the old production plan right now. Okay? All right, so what is the objective function value? So the objective function value of this solution, of this feasible solution, in the new problem is given by, well, I'll just plug in that solution into the objective function. Okay? So what do I get? Well, x is the same as x star, so I will get c times x star. And xm plus 1 is equal to 0, so I'll just get c times x star, which is precisely the same as the optimal solution, optimal value of the original problem, right? So it's given by c times x star plus cm plus 1 times 0. So that's the same as cx star, i.e. the optimal value of the previous problem. And again, intuitively this should make sense because I'm just using the same production plan as before, so my profit should be the same basically, right? Okay, my profit does not change. Okay, so any questions so far? All right, yes?
This solution can be also the best feasible solution.
For the new problem. That's a good question. So,
We choose not to produce a product example.
exactly. So now there are actually two possibilities, okay? So the first possibility is that the previous production plan actually remains optimal for the new problem as well. That's the first possibility. Or I can find an even better production schedule with the new product. Okay, so that's going to be second possibility. Okay, and if we're going to look at each possibility in turn, so either x bar is optimal for the new problem, optimal for p prime, or there exists a better feasible solution for the new problem. So now that brings us to the next question, basically. And again, this is, in a sense, the heart of sensitivity analysis, just to make sure that you really understand this topic. So here's my question. So under which circumstances is the new solution optimal for the modified problem? Okay. So when is it the case that I'm not going to change my production plan because that's going to be still optimal? So when? Under what circumstances will that be the case? So let me repeat my question again. So I have an optimal solution for the original problem. I constructed a feasible solution for the new problem based on the optimal solution of the original problem. And that new solution may or may not be optimal for the new problem, right? So I know that it's feasible, okay? It can be the best feasible solution or not, basically, okay? My question is the following. So under what conditions will it be the best feasible solution? And under what conditions will it not be the best feasible solution? Yes?
Cm plus 1 is negative, we don't produce.
If Cm plus 1 is 0, if the basic variables still remain basic, so that the CB doesn't change, or C.
Well, okay, so let's think about it. So does CB change, actually? Well, I'm just using the same basic variables, right, as the previous one. So my CB actually stays the same. Okay? Now let's try to think of this in terms of the simplex tableau. Okay? So what's the difference between these two problems? Well, the difference is that now I have one more variable, basically, right? So which means that in my simplex tableau, I'm going to need one more column, right, corresponding to a variable. Okay? So which means that, so as a result, I need to add a new column to my simplex tableau, okay, corresponding to xm plus 1, basically. Is everybody following? Okay. And obviously, primal feasibility is not affected, basically, right? Because I'm not changing the values of my variables, okay? My b is the same, my capital B is the same as well. CB does not change because I'm using the same variables as the original problem, same basic variables, okay? So the right-hand side value does not change. So the only thing that I need to worry about is the following. So now I'm going to have one more element in row 0, basically, right? Okay? So I'm going to have one more component in row 0. And that component will correspond to the row 0 coefficient of xn plus 1. Okay? So then if I look at the new problem, if the row 0 coefficient of the new variable is non-negative, okay, then this solution is still optimal, basically, right? If the row 0 coefficient of xn plus 1 is negative, basically, so then that means that if I increase xn plus 1 from 0, from its current value of 0, then my objective function will improve, actually. So I'm going to find a better solution. Does that make sense? Yes?
But if Cn plus 1 is positive at first, but in the simplex method, in the time it gets negative, so we can change it.
Okay, so once again, one thing you should be careful about is the following. I'm not really interested in Cn plus 1 directly, but what I'm interested in is the row 0 coefficient of that variable, which does depend on Cn plus 1. Okay? So as a result, rather than what Cn plus 1 is, I'm actually interested in what the row 0 coefficient of xn plus 1 is, basically. Okay? So that's actually more important for me. Okay? So that will determine whether I should actually enter xn plus 1 or not. Okay? Yes?
Can we say if xn plus 1 doesn't turn to be a basic variable and the basic variable stays same, x b's, can we also be correct for the answer of this question?
Well, so the problem is the following. So what you're doing is you're just sort of changing the wording of my problem. Okay? So you're just sort of asking the question in a different way. Okay? So you're saying that if the basic variables do not change, then of course the same solution will be optimal. Well, my question is, well, when do the basic variables not change? So that's my problem. Okay? So it's not a question of, if it changes or not. So it's a question of when it changes, basically. Okay? When does it change and when does it not? So now let me just go back to the dual problem now. Okay? Now in the original problem, I know that W star is an optimal solution, right? So W star satisfies all of these conditions. And W star B is the same as CX star, right, by strong duality theorem. Okay, the optimum values are the same. Now let me look at my new problem. Okay, so in my new problem, I have this additional constraint that I didn't have before, right, in the original problem. So there are two possibilities. W star may still be feasible for this problem. Okay, so W star may still satisfy the new constraints. Okay. And I claim that if that is the case, then that solution x bar will still be optimal for this problem. Okay? Let me repeat it again. So if I take W star, which is the optimal solution of the original dual problem, and if I plug it into the new constraint here, okay, I know that W star satisfies this one. W star satisfies this one as well because they're the same as the previous constraints. Okay? So the only thing I need to worry about is this new constraint. And there are two possibilities. So the first possibility is that W star may satisfy the new constraint, okay? Or W star may violate the new constraint, obviously, right? So there are two choices. So I claim the following. If W star satisfies the new constraint, okay, then I claim that that solution is optimal for the new problem, basically. Okay? So let me write it down. If W star satisfies the new constraint, new constraint given by W am plus 1 greater than or equal to Cm plus 1, then x bar is optimal for the primal problem, for the new primal problem, for P prime, and W star is optimal for the dual problem. For the new dual problem. And my question is the following. So why is that true? So can somebody tell me why that should be true? So here is a hint. I have a feasible solution for the new problem, which is given by x bar. And I also have a feasible solution for the dual problem. Okay? So what can I say about the corresponding objective function values? Well, what's the objective function value of that feasible solution? It's just same as Cx star, right? What's the objective function value of that solution? W star B. And what do we know from the previous problems? That they are the same, basically, right? Okay? Well, so what do we have? Well, I have a feasible solution for the primal problem, for the new primal problem. I have a feasible solution for the new dual problem, and their objective function values are the same. So what can I conclude? That they should be optimal. Okay, so this follows from strong duality theorem, since the two objective function, the primal and dual objective function values are the same. Objective function values are the same. Values are the same for the new problems. Is that clear? So is the last part clear? So essentially what I'm saying is the following. So I know that x bar is a feasible solution for P, okay? And I know that the objective function value of x bar is the same as Cx star. We just computed that here, okay? And now I'm assuming that W star satisfies this constraint, the new constraint, okay? So in that case, W star is a feasible solution for the new problem as well. And the corresponding objective function value is given by W star B, which is precisely the same as the optimal value of this problem, okay? And the objective function value here is Cx star, so which means that by strong duality between the original pair of problems, the optimal values are the same. The objective function values are the same. Then by strong duality, I know that x bar is optimal for this one, and W star is optimal for this problem. Yes?
Hocam şimdi orijinal probleme eklediğimiz variable dualiminde bir tane şey oluşturuyor, constraint oluşturuyor ya. Bu constraint dualinin optimumunu değiştirmediği sürece o orijinal probleminde bu optimumu değişmeyecektir demek. Yani bu buraya gelecek olsak yani dualinde oluşan constraint eğer unnecessary bir constraint ise optimalımız değişmez diyoruz.
Region değiştirmezse
Yani evet, ya da region değiştirmezse.
So what I'm saying basically is the following. Adding a new variable to a primal problem is equivalent to adding a new constraint to the dual problem. Okay? So as I said, the feasible region of the new problem cannot be larger than the feasible region of the original problem. Okay? Now what I'm saying is the following. If the new constraint is such that it is satisfied by the old optimal solution, then the optimal solution of the dual problem does not change. That's what I'm saying basically. Okay? And then by strong duality, I know that I have a feasible solution whose objective function value is the same as the optimal value here. So as a result, x bar should be optimal for this problem. Okay? Now here's another way to see this, basically. So let me look at W star times am plus 1 minus C1. Cm plus 1. So essentially, I'm looking at the new constraint, and I'm just putting everything on the left-hand side. Okay? Now, if you remember from strong duality, so we know what W star is basically, right? So if I have an optimal basic feasible solution for the primal problem, then based on that, I can compute W star. Do you remember that? So W star has a closed form expression basically, which was given by CB times B inverse, exactly. So as a result, I can replace W star by CB times B inverse, AM plus 1, minus CM plus 1, basically, okay? Now, what does this look like? What does this expression look like? Well, this is nothing but the row 0 coefficient of xm plus 1, basically, okay? So if this is greater than or equal to 0, that means that the row 0 coefficient of xm plus 1 is non-negative, which means that my current tableau is still optimal, basically. Okay? Well, this is precisely the same as, well, if this is non-negative, then W star am plus 1 minus Cm plus 1 is non-negative, which implies that W star times am plus 1 should be at least as large as Cm plus 1, which is exactly this constraint right here, basically. Okay? So, which means that if W star satisfies the new dual constraint, then the row 0 coefficient of xm plus 1 is still non-negative. So, which means that my current tableau will still be optimal. So that's a relationship between the dual problem and the simplex tableau. Is that clear? So as I said, this is nothing but the row 0 coefficient of xm plus 1. And as long as that number is non-negative, I know that my previous solution will still be optimal for the new problem. Okay? And another way to think about this is the following. So if W star satisfies this new constraint, then I maintain dual feasibility. Okay? And maintaining dual feasibility is the same as having non-negative coefficients in row 0, basically. Okay? Is that clear? So, all right. Okay, so what if W star does not satisfy the new constraint? Well, then I cannot use W star as a feasible solution for the dual problem. Okay? In other words, so this number now becomes less than 0. Okay? But this is nothing but the row 0 coefficient of xn plus 1. So I need to introduce xn plus 1. Okay? I need to enter xn plus 1, and I need to continue with the simplex. Okay? So one way to think about this is the following. So if the original dual solution does not satisfy the new constraint, then my current production plan cannot be optimal. Okay? In which case, I'm actually better off starting to produce the new product in some sense. Okay? xn plus 1 is currently 0. But if I increase the value of xn plus 1, then I'm going to achieve a better product. Better profit, sorry. Is that clear? So that's the intuition, basically. Okay? All right. So as I said, if W star does not satisfy the new dual constraint, then the row 0 coefficient of xn plus 1 is negative. So this implies that x bar cannot be optimal. Then we're going to enter xn plus 1 and continue with which version of the simplex? Continue with the regular or the primal simplex, okay? Continue with the primal simplex. Why do we continue with primal simplex? Because we still have primal feasibility, right? So we don't have dual feasibility, but we have primal feasibility. So we're going to try to attain dual feasibility again. So let me give you an example. So this is the same example from last time. I'm going to write it once more. So suppose that we have a maximization problem. I want to maximize 60x1 plus 30x2 plus 20x3. And here are my constraints. So 8x1 plus 6x2 plus x3 is less than or equal to 48. Then 4x1 plus 2x2 plus 1.5x3 is less than or equal to 20. And finally, 2x1 plus 1.5x2 plus 0.5x3 is less than or equal to 8. And all of my variables are non-negative. So this is the same problem that we've been using over and over again. Okay? And then I'm going to give you the optimal tableau once more. So I have my original variables followed by the slack variables. And row 0 looks like the following: 1, 0, 5, 0, 0, 10, 10, 280. And then I have 0, 0, minus 2, 0, 1, 2, minus 8, and the right-hand side is 24. Then 0, 0, minus 2, 1, 0, 2, minus 4 and 8. And finally 0, 1, 5 over 4, 0, 0, minus 1 over 2, 3 over 2, and 2. And the basic variables are, I have x4, x3, and x1. So this is the optimal tableau, optimal simplex tableau for this problem. Okay? And think of it, if you think of this as a production planning problem, so currently I have 3 products, basically. Okay? And I have 3 resources that I need to produce these products. So what I'm going to do is I'm going to now assume that I'm going to introduce a new product. Okay? So since I'm using x4, x5, x6 as my select variables, I'm going to call the new variable x7, basically. Okay? So So suppose that we introduce a new variable, x7, and with the corresponding column, which I'm going to do by A7, is given by 1, 1, 1, and I also need the cost coefficient, and the cost coefficient, let's say, is given by 15. So think of this as my new product, whose profit is 15, and its resource usage will be 1 for the first resource, 1 for the second one, and 1 for the third one. Okay? The reason why I'm using x7 is because I'm using x4, x5, x6 as a slack variable, so x7 is the next one, basically, okay? And the question is the following. So, is the current Tableau still optimal? Well, so, I mean, if you think about the discussion that we had earlier, so the optimality of the previous solution actually depends only on one thing, okay? And that thing is basically whether W star is still feasible for the new dual problem, okay? In other words, whether the row zero coefficient of x7 will remain non-negative or not, okay? So I just need to compute the row zero coefficient of x7. So what is the row zero coefficient of x7? So I have CB times B inverse times A7 minus C7, basically, right? So this is precisely the formula that I'm going to use. All right, so what is CBB inverse? Well, we've seen this over and over again. So it's precisely given by the row zero coefficients of slack variables. Okay, so I have 0, 10, 10, which is precisely my W star, basically. So this is also my W star. And I'm going to multiply it by A7, which is 1, 1, 1. And from that, I'm going to subtract C7, which is equal to 15. And what do we get? So what's the inner product of these two vectors? I have 0 plus 10 plus 10, so I have 20. 20 minus 15 is 5. And 5 is greater than 0. So what do I conclude? So it's still optimal, basically, right? The row zero coefficient of x7 is still positive, or non-negative, basically. So which means that my previous dual solution satisfies a new dual constraint corresponding to a new variable. So as a result, my optimal solution does not change. Okay? So the current solution remains optimal by simply defining x7 to be equal to 0. So in this case, one way to think about this is the following. So this new product will not be profitable enough to start production, basically. Okay, I'm going to still stick with the original production plan. Okay? All right, so let's look at another part. So what if A7 is still the same, let's say 1, 1, 1, but C7 is, let's say, this time equal to 25. Well, I'll just sort of check the same thing, basically. Okay, so I'll just compute the row zero coefficient. Again, I'll just have 0, 10, 10 multiplied by 1, 1, 1 minus C7 is equal to 25. And now I get minus 5, and minus 5 is strictly less than 0, basically, right? So what's the implication of this? Well, my original dual solution is not feasible for the new dual problem now. Okay? So in other words, I'm actually losing dual feasibility. Okay? So which means that the current solution cannot be optimal anymore. Current Tableau cannot be optimal. So I need to set up my Simplex Tableau, and I need to continue, basically. Okay? So one thing you should be careful about is the following. So now I'm going to have the original Tableau followed by my new variable. Okay, so I just computed the row zero coefficient of x7. So I'm going to just put minus 5 over here, basically. Okay. What else do I need? Well, I also need to compute the entries underneath x7. Okay. So if I go back to my generic Simplex Tableau, so So those components are given by B inverse times A. Okay? And since I only need the entries underneath X7, so what's the corresponding expression for the entries here? So I'm going to multiply B inverse by the column corresponding to X7, basically. Okay? And the column corresponding to X7 is given by 1, 1, 1. Okay? So I need to compute B inverse times A7. So here's the second $1 million question. So what is B inverse? So you just need to look at the entries under the slack variables, basically, right? So that's important. So this is my B inverse. And this is my CB inverse. So I'll just copy my B inverse from there. So I have 1, 0, 0, 2, 2, minus 1 over 2, and then minus 8, minus 4, 3 over 2. And I'm going to multiply by A7, and A7 is given by 1, 1, 1. Okay? So what do we get? What's the first component? 1 plus 2 is 3 minus 8, so I get minus 5. Okay? So 2 minus 4, I get minus 2. And then 0 minus 1 over 2 plus 3 over 2, I get 1, basically, right? Okay? So what am I going to do? Well, I'll just take these numbers and put it in my simplex tableau. So I have minus 5, minus 2, and 1, basically, okay? What about the remaining parts of the tableau? Well, they're going to be exactly the same as those numbers, so I'm not going to write them down. Okay? So what am I going to do? I'm going to enter X7. Okay? And which variable will leave in this case? Well, there's only one variable eligible for the ratio test, and that variable will leave the basis and continue with the primal simplex. Okay? So as a result, if you add a new variable to an LP problem, there are two possibilities. Either your previous solution stays the same by defining 0 for the new variable. Okay, so that's the first possibility. The second possibility is that the optimal solution changes, in which case you need to enter the new variable and continue with the simplex, the primal simplex. Okay. So one way to think about, again, this is the following. So if this number, which is the row zero coefficient of X7, is non-negative, then my current solution is still optimal, right? So one way to think about this is the following. So the inner product here is 20, basically, right? So as long as C7 is less than 20, less than or equal to 20, then this number will be non-negative. Okay? So if C7 is larger than 20, as in that case, then the solution will change. So as a result, one way to think about this is the following. So as long as the profit of my new product is less than or equal to 20, then I'm going to stick with my original production plan. Okay? If the profit of my new product is larger than 20, then it makes sense to start producing new product instead of the old products, basically. Okay? So, I mean, think of that as a threshold value, basically. Okay? So if the profit is larger than 20, then it makes sense to start producing the new product. If it doesn't, then it's not profitable to change my production plan. Okay? And of course, that does depend on the value of C7, okay, the cost coefficient. Okay? But not directly. It depends using this expression right here. Any questions? Yes?
C7 was 20, it will be 0.
Uh-huh. That's a good question. So if C7 is equal to 20, then this number will be equal to 0, basically, right? So which means that the row zero coefficient of X7 will be 0. So what does that mean? You tell me. The optimal solution is the same, but there are basically alternate optimal solutions in that case, right? Okay? So in that case, I can also enter X7 without changing the profit, basically, okay? So in that case, there will be an alternate production plan in which I'm going to produce X7 as well, okay? But I may still stick with the old production plan. That's the message. Okay? All right, so let me just start the second part, then we'll take a break. So far, we have looked at what happens if we add a new variable. What about adding a new constraint? So once again, let me start with my primal problem. So I want to maximize a linear function subject to linear equality constraints and non-negativity. And then corresponding dual problem will be a minimization problem. So suppose now that I'm going to add a new constraint to my problem. So I will have the same number of primal variables, ax less than or equal to b. But I'm going to introduce a new constraint, which I'm going to denote by d times x is less than or equal to d bar. So think of d as a row vector. And I'm multiplying row vector by a column vector, so this is just a single number. And this is another single number, basically, okay? And x is still non-negative. Now, what is the corresponding effect on the dual problem? Well, now, unlike the previous case, the number of constraints is increasing, right? So the number of constraints in the primal problem has increased. What's the effect on the dual problem? Exactly. So now I'm going to need one more variable for the dual problem, basically, okay? So let's think about the new dual problem. So I'm going to use w again for the original constraints. And for the new constraint, for the new single constraint, I'm going to need a new single dual variable, which I'm going to call w bar, okay, just to make it consistent with the notation. So what does the new objective function look like? I'm going to have wb plus now the additional term. So what's the additional term? W bar times d bar, basically, okay? Now, what are the constraints? WA plus W bar D is larger than C, basically, right? Okay? And W is non-negative, and so is W bar. Okay, both W and W bar is non-negative. So W is a row vector. Okay, W bar is a single number. Okay, and if you look at, for example, this constraint, so W times A is a row vector. W bar is a single number, but D is also a row vector. So I'm adding up two row vectors here, and they should be greater than or equal to another row vector, basically. Okay, so dimensions actually are fine. So let me just mention the symmetry again between the primal and dual problems. Well, if I add a new primal variable, that corresponds to adding a new dual constraint. If I add a new primal constraint, that corresponds to adding a new dual variable, basically, right? So there's a perfect symmetry between the two problems, basically. So now I'm actually changing the feasible region of the primal problem, and I'm actually adding a new variable to the dual problem. Okay? So the effect of adding a new constraint actually corresponds to adding a new variable for the for the dual problem. Sorry. Okay? All right. So let's take a break. We'll continue.